Have you ever just looked around? At the room you're in, the building. It all seems so solid, right? So still. But here's the thing, it's not. It's in a constant, invisible fight for survival. Today, we're going to pull back the curtain on the hidden art that keeps our world from falling apart. Structural equilibrium.
You see, every single bridge you cross, every skyscraper, it's in a constant, invisible fight. Gravity is always pulling down, wind is trying to push it over, even the sun gets in on the action, trying to bend it with heat. These things aren't just static objects. They are in this perpetual, delicate dance of balance.
So what are these secrets? What are the invisible forces holding everything together? Well, that's what we're here to do. We're going to uncover the absolute core principles that let us build these incredible marvels that scrape the sky and leap across oceans.
Okay, so how does it all actually work? It's kind of wild, but when you boil it all down, every single structure, I'm talking from an ancient Roman arch to the tallest skyscraper today, it's all just a negotiation between two and only two fundamental forces.
And here they are, compression and tension. One is a pushing or squeezing force, the other is a pulling force. That's it. Every building, every bridge you've ever laid eyes on is just a super cleverly designed dance between these two.
All right, so let's start with compression. It's really just a fancy word for squeezing. The classic stone arch, it's the perfect poster child for this. Each stone is constantly trying to push its neighbors inward, and that collective powerful squeeze is what magically channels all that weight down to the ground. It's what gives the arch its amazing strength.
And then you've got its opposite, tension. This is all about pulling things apart. Think about the huge steel cables on a suspension bridge. I mean, those things are stretched insanely tight, literally hanging the entire weight of the road from the towers above. That is tension in its purest form.
Okay, so engineers get compression and tension. But, how do you take that knowledge and build something that can stand up to the raw, brute force of nature? Well, this is where the real genius comes in, planning for the absolute extreme.
One of the most important ideas in all of engineering is something called the factor of safety. And honestly, it's pretty simple. Engineers are, by nature, a pretty cautious bunch. They would never design something to hold exactly its expected weight. They always over-engineer it. They build in a buffer for the stuff you can't predict.
You know the sign in an elevator, right? Max 10 people or whatever? That number? That's not the point where the cables snap. No way. It's the safe operating limit. Thanks to that factor of safety, those cables are built to hold way more weight than that. It's all about having a backup for the what-ifs.
But okay, a few extra people in an elevator is one thing. What about something bigger? How does a massive skyscraper literally fight off the fury of a typhoon? The answer is, well, it's actually kind of brilliant, and it is mind-bogglingly huge.
660 metric tons. Let that sink in for a second. To give you some perspective, that's about the same weight as 100 full-grown elephants. Yeah, 100. So what is this thing? High up inside the Taipei 101 tower, there is this massive steel ball just hanging. When a typhoon pushes the building one way, this giant pendulum, it's called a tuned mass damper, it swings the other way. It's basically a giant counterweight. It's designed to cancel out the building's natural swaying motion to stop it from getting out of control. It not only keeps the building standing, but it also stops the people inside from getting seasick. And this brings us to a really surprising secret of great engineering. Being too stiff is actually a bad thing. Rigidity can lead to failure. To survive, big structures have to breathe. They have to be flexible. The Eiffel Tower literally grows by up to 15 centimeters in the summer heat. And the Burj Khalifa, the tallest building in the world, its tip is designed to sway 1.5 meters, almost 5 feet, just to confuse the wind and shed all that force.
And there is probably no better, more beautiful example of this whole idea in action than our big case study, the Golden Gate Bridge. It is an absolute masterclass in managing tension and compression on a scale that is just staggering.
So how does it work? The genius is all in what engineers call the load path. Basically, the journey the force takes through the structure. Okay, so follow the load with me. The weight of all the cars, it hangs from those skinny-looking vertical cables. Those cables pull straight down on the two enormous main cables, stretching them out. That's pure tension. Then, those main cables pull inward on the giant towers, squeezing them. That's pure compression. And finally, the towers take that entire colossal load and dump it safely into the ground. It's so elegant.
But wait a second. What stops those two towers from just getting pulled together by all that insane tension? That's where these massive concrete blocks come in, the anchorages on either shore. And this analogy from the source material just nails it. It says, the massive concrete anchors act like a person leaning back in a game of tug-of-war, using their weight to pull against the bridge's load. Isn't that a perfect picture?
But the bridge's real party trick, its secret weapon, is its flexibility. Get this. Under the right load and temperature, the road itself can move up and down by as much as 10 feet. That's like the height of a basketball hoop.
But hold on, that's nothing. When those powerful Pacific winds really get going, the bridge is designed to sway from side to side by an incredible 27 feet. 27! If that bridge had been built to be perfectly rigid, it would have shattered into pieces decades ago.
You know, it's easy to look at something like the Golden Gate and think it's this pinnacle of modern tech. And it is. But the basic ideas behind it? They are absolutely timeless. The entire history of engineering is really just the story of humans getting better and better at taming these exact same forces over thousands of years.
And this table shows such a cool contrast in how to solve the same problem. On one hand, you've got the Golden Gate. It's all about this elegant, sophisticated dance between tension and compression, which lets it be light and flexible. And then you've got the Great Pyramids. Their strategy, pure brute force compression. They basically win the fight against gravity by just being so ridiculously heavy and solid that nothing can move them. Two totally different philosophies.
And you can really trace this evolution right through history. You start way back with the pyramids, the ultimate monument to just stacking stuff up really well. Then you have the Romans, who started getting really clever with new materials, like concrete in the Pantheon. And then, fast forward a couple thousand years, and we finally crack the code on tension, which lets us build these incredible, lightweight, flexible structures, like the Golden Gate.
And hey, speaking of the Romans, we have to talk about their concrete. It was seriously like something out of science fiction. They figured out that if they mixed volcanic ash into their concrete, it created a material that could literally heal itself. So when little cracks would form and water got in, it would kick off a chemical reaction that would fill the crack back in, making the whole thing even stronger. I mean, come on, that is unbelievable. A building that fixes itself.
So, in the end, every single structure out there is telling a story. It's a story about a quiet, constant negotiation between pushing and pulling. It's this beautiful, delicate ballet between stability and movement, between the need to be strong and the need to be flexible.
So the world we've built around us, it's not just a bunch of lifeless objects. It's alive. It's breathing with all these pushes and pulls. So here's my challenge to you. The next time you walk outside and look up at a skyscraper or drive over a bridge, what invisible forces will you see?